Could another Big Bang happen within the universe? Is dark matter falsifiable? And is there room in the Lagrange points? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, the question pops into your brain. Just write it down. We'll gather them up and I'll answer them here. Now, I get this question all the time, like where do we ask these questions? And ironically, when a person asks the question, about where to ask the question, they've already found the place to ask the question. And that is wherever you feel is the right place to ask the question. So my preferred place is in the YouTube comments, but obviously if you're a Patreon, go ahead and put it into the Patreon comments. Don't email me. It's just not like if you send me an email, then I may answer you, but if you post the comment in the YouTube, then maybe I don't get a chance to answer, but lots of other people can jump in and give you more information as well. So it's better to have conversations in public than to send a private message, just because then lots of people can enjoy the answer to the question, even if I'm not the one who gives it. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to participate in the live show, ask your question, get follow-up questions, stick around for overtime, which is now just becoming really big. The overtime part of the live show is as long as the regular show, even longer sometimes. So you're seeing about a third of the actual question show at this point. So definitely come join the live show and stick around for overtime. All right, let's get into the questions. Baby Macker. Would it be better for finding near-Earth objects to have a constellation of satellites at supersynchronous orbit than just Earth-bound telescopes? Yes. I took off my sweatshirt. It was getting really hot. Right now, astronomers know about 14,000 near-Earth objects that are about 100 meters across, to 140 meters across. And these are considered dangerous. That if one of these struck the Earth, it would airburst or strike the ground and cause an enormous amount of destruction on a regional level. There are also about 1,000 1-kilometer asteroids, but astronomers have mapped out most of them. But for the smaller ones, the ones that are in the sort of 140 meter range, they estimate that there's still about another 15,000 of them out there. So they only know of about half of them. And there's a couple of problems with finding these objects. They are smaller, and so they are dimmer. And so they're just harder to find, even though they have the potential of coming close to the Earth. But the other problem is that you're looking for them in the wrong wavelengths. So an asteroid is dark. You saw the pictures of the sample capsule from OSIRIS-REx. It's like crushed up charcoal. And so they don't reflect very much light from the sun at all. But what they do is glow in the infrared. And so the best way to be able to see these objects is to be able to see them in the infrared. Now, the other problem is that some of the most dangerous, kind of the scariest ones that are out there are the ones that come at us from the sun because we have no warning. So imagine you've got an asteroid that has an orbit that is inside the orbit of the Earth. And so pretty much the entire time that you're looking for it, you're having to look sort of from sort of close to the sun to at the sun. And there's a limit to what you can see. And so you can imagine there could be asteroids that are on a collision course with us and they're just coming straight out of the sun at us. And so we just won't be able to see it in time. So to solve both of those problems, you want to go to space. And ideally, you want to get away from the Earth. You want to get to another perspective. So in other words, what might be coming out of the sun from the Earth is not going to be coming out of the sun from, say, the L4 or the L5 point. From that, you're seeing it off coming in from the side. And then you want to have an infrared telescope that's going to map all of the objects in the vicinity. So there's an upcoming mission that is going to do parts of this. And this is called the Near Earth Object Surveyor mission. And this is going to be launching in 2028. And it's a NASA mission. And the plan is to use this infrared capability from space to map out as many of the objects as it can. And the hope is that they'll be able to fill in all of those missing pieces. So you want to be in space, you want to be infrared, and you want to be able to observe the sun, ideally from a different angle than the Earth is, to be able to map out as many of these objects as possible. But the good news is that with this and with other follow-on observatories, we'll get to a point where we've mapped all the 1 kilometer objects, all the 100-meter objects, all the 50-meter objects. And then all that's left are the objects that are just too small, not that dangerous. Like think about, say, Chelyabinsk-sized objects that will detonate and smash all the windows in a city, but they won't necessarily take out an entire city the way a larger object could. You probably noticed the planet name that has appeared above my shoulder. This is a way for you to vote and tell us which of the questions you thought was the best. And this week, or last week, the answer was from Sandy VB, wondering how we get a flash of neutrinos from a supernova that arrived before the light from the supernova itself. So thank you everybody who voted for that question. And so remember, just watch the rest of this video, pick the planet name that matches the question that you think is the best, or the answer, or whatever, and go ahead and put that in the comments down below, and I will gather them up next week and we will celebrate it here. Thomas Sidoikis, what do you think about using artificial intelligence in space exploration? Something like a live AI pilot to land spacecraft? Yeah, using artificial intelligence for space exploration is one of the best applications that I can even think of. That when you think about how far away it is, even just to get to Mars, you know, if you want to send instructions to your spacecraft, you're going to take 4 minutes, 20 minutes. Like, it's going to take a while to send communication to your spacecraft. If you want to have your Titan helicopter flying around, you're going to be looking at an hour plus delay to just send messages back and forth. It's got to be able to make decisions on its own. And we actually saw a pretty neat sneak preview of this with the Mars Perseverance rover. When it landed at Mars, as it was entering the atmosphere, it was taking its own pictures of the surface of Mars. It knew where it was supposed to land roughly, but it actually imaged the landscape, mapped out all the features, compared it against what it knew, made sure that there weren't any big problems, and chose its landing site. And that was a first. And you're seeing more work being done to figure out how, like, rovers can move across landscapes, making decisions autonomously on their own. You tell them, like, get to the top of that mountain, and it figures out all the nitty-gritty details. And you're going to see that play out more and more as these spacecraft are farther from Earth. Our computers are getting better, and I think it's going to be great that engineers can give the goals without having to micromanage every single movement that the spacecraft does. Chris Scott, could another Big Bang happen within our universe? And if so, what would it look like? Well, so we don't know what created the Big Bang. We don't know what were the conditions that caused the Big Bang. All we know is that right now, when you look in all directions, you see galaxies moving away from you. And if you looked back in time, the galaxies would be closer and closer together. And there was a time when all the galaxies that we could see were no longer galaxies, but were actually this gluon plasma soup of particles right moments after the beginning of the universe. But if there's an infinite amount of time ahead of us where the universe is just going to keep expanding and keep expanding, then some really weird things are possible. So we think about this idea of entropy, that if you're in a room, all of the air particles are collected together in the room with you. And that is like, you know, that's the probability of all of those particles that they are in the room. And that's what's most likely, but there's a really slight chance that all of those particles could suddenly teleport and be somewhere else, like say Mars or in Andromeda or halfway across the observable universe. The possibilities are extremely low, but they're not zero. And so once you think about infinity, if you just keep waiting longer and longer times, eventually really improbable events will start to happen. In fact, they will happen an infinite number of times. And this leads to this idea of Boltzmann brains, that if you wait long enough, then a conscious being will appear in the universe, complete with all of the memories of a life well lived, and they will exist for just a moment in an uncaring universe before they, I guess, wipe out. And they will have observed the universe, and they will think that they've been around forever, and that they remember telescopes and everybody was looking through the sky. And sort of one of the really kind of weird paradoxes is that, like, maybe, you know, if there is an infinite amount of time into the future, then the vast majority of entities that are experiencing the universe are actually these Boltzmann brains. And I'm not going to go too deep into it. I mean, it's sort of like, it'll blow your mind. But if you keep going along on the probabilities, you know, when we think about all of the matter that is in the observable universe, there is a probability that all of that matter and energy and everything that's in the universe is expanding away from each other at this ever increasing rate. But if you wait long enough, then the probability is that all of what is now the observable universe was once a singularity. And so you can kind of mathematically predict how long you would have to wait before you got another Big Bang, just through random chance based on all of the stuff that's in the universe today. But it's a big number. Mickey Melnick 2230. Am I the only one who really misses the weekly space hangout? So for those of you who are new, we used to do a show over on another channel called the Weekly Space Hangout, where me and a bunch of space journalists would get together in a round table and present various news stories, and then we'd bring in a special guest, and it was a lot of fun. And we had a dedicated following, and you know, many of the people that are in the chat here were in the chat over there, and I miss it too. But Nancy Graziano was the glue that kept the machine running, and she was just getting burnt out as a volunteer, and so she had to say, like, I can't do this anymore. And we're like, well, we're kind of making the show for you, Nancy, so we'll probably have to wrap the whole thing up. And this is like just like, I have lots of great ideas, but the best ideas, the ones that can stick around, are the ones that are possible to be done. And trying to herd a big group of people every week, a rotating group, like, was just so much energy and work. And so I've tried to bring a lot of the pieces of the Weekly Space Hangout into what I do here on my YouTube channel. So there's a couple of things. One is I do a lot more interviews. I do a lot more kind of in-depth, long interviews. You know, so before we were doing maybe 15-minute interviews on the Weekly Space Hangout, but now I do like hour-long interviews. The production quality is a lot higher now. So like, I'll record them offline, we edit them together, we put in graphics. Like, hopefully we've nailed interviews here on the channel. But the thing, and then the other thing, is having these kind of roundtables. And if you've noticed, I've done a bunch of these roundtables now, like 3 or 4. I did one with Scott Manley and Marcus House. I did one with Jesse Christensen and Space Mog. And I've done, I think, another one and with Antron Petrov and Joe Scott. And it's a lot of fun. And I plan to do more of that. And so probably once a month or so, we'll figure out some kind of roundtable conversation where I can pull together some other journalists and talk about this kind of stuff. The piece of the puzzle that I haven't been able to figure out, and you know, if you have some suggestions for me, I'm all ears, which was that we gave practice to aspiring space or science communicators. It was a place where a person who wants to be a science communicator, who wants more practice, like maybe they're a scientist, but they want more practice giving talks or being able to explain the science that's being done, a place where, you know, like, I'm knowledgeable enough to ask questions, but also to kind of manage the time and have these conversations with people. And it was a way to give people just practical experience when it's so hard. Like, who wants to bring you on as a commentator if you don't have a lot of experience? I mean, you look at the additional experience that many of the alumni from the Weekly Space Hangout went off to have. Like, it felt really proud. And so I want to figure out a way to give people who are new in their career, but who have an interest in being a science communicator, a platform to do that. And so I haven't figured out the version of that is easy for them, doable for me, is good, interesting for you as an audience. So if anyone has any recommendations, some suggestions for like what would be a format or something that you would like to see, just put it into the comments, and I would love to figure out a way to do it. Anyway, that's it. I don't know the solution, but I agree. I miss it. And I miss not being able to help people get practice being science communicators. Jackalope839. Has anyone proposed a falsifiable dark matter prediction? Is dark matter just silly? Like, dark matter is a collection of observations, and I've been thinking about how we could do some practical experiments to show how dark matter works, what the observations are. And so I've got a couple of ideas. One is that we like set up like a potter's wheel and we put sand on top, and then you spin the potter's wheel and then the sand will sort of spread out across the potter wheel and then sort of spray off, right? And that's the galaxy rotation problem. And yet if you then put something like, say, sandpaper on the potter wheel, or maybe you put glue on the potter wheel and then you turn the potter wheel at the same speed and the sand would spread out, but it would stick to the top of the potter wheel. And so like, that's the difference. Like when astronomers observe galaxies and they observe them rotating, they should just fall apart, but they don't. And so like either there's more stuff pulling it together with its gravity that we can't see, or we don't understand how gravity works at a galactic scale. Like that alone is a puzzle that still astronomers haven't been able to work out. But then when you look at the orbits of stars inside the galaxy, when you look at the solar system, Mercury goes around really quickly, 48 kilometers per second, but Earth goes 30 kilometers per second, Neptune goes 5 kilometers per second. Like the closest planet is going around and around and around, the farther planets are going a little slower, and then at the outskirts of the planet, they're going very slowly around. And that is what you'd expect if you've got the sun as the mass at the heart and you do the math for either general relativity or even Newton's equations, you get those numbers. And yet when you look at the movements of stars in a galaxy, you get very rapid rotation close up, but then you reach this point where the rotation speed is the same. And as you go farther out in the galaxy, the rotation speed is the same. As you go farther out in the galaxy, the rotation speed is the same. That's like not what you would expect. And so once again, like how do you get that? You would have to have more mass in that galaxy for it to have this. They call this the Keplerian cliff. And you can mark this spot in a galaxy where you would expect the rotation speed of the stars, or the orbital speed of the stars, to drop precipitously, to slow down, but it doesn't. It just plateaus off, and the gap is enormous. And like, explain that, right? And so another kind of practical effect is to like think about gravitational lensing. So the description that I always think about is like, imagine you're at the bottom of a pool and you're looking up at trees above you, and you know what the trees should look like if you were just like, if there's no water in the pool, and yet you're seeing the trees kind of wobble back and forth as the light rays are coming, from the trees through the water, and they're hitting your eyeballs. And so you can go, well, there has to be some fluid, some transparent fluid in between me and those trees, because I can see those trees are moving in ways that trees just don't move. And so you could actually calculate the amount of transparent fluid that is in between you and those trees. And so like I was sort of thinking about like, what if you had like lenses just hanging in the air, and then you took a picture of something and then you could see the spots where the lenses are. And so when astronomers map out the night sky, they see these warps in space coming from nowhere. Like you're seeing this gigantic warp of light, where light is clearly being bent and twisted. And in some cases, light gets broken apart into, like, if you've got like some background galaxy and you got some foreground galaxy, and then the light is being broken 4 times coming around the foreground galaxy to create this thing called an Einstein cross. And you wouldn't get that just with the mass of the galaxy itself. You can only do that with some other amount of mass, and that amount of mass that you would need to get that gravitational lensing matches the amount of mass that it would take to make this galaxy rotate without falling apart, which matches the amount of mass that you would need to have the stars follow these paths. And then there's another thing, this is the tricky one, is the cosmic microwave background, where you can kind of imagine a sheet, and you can imagine, like, all the different color variations in the cosmic microwave background. They match over and under densities in the beginning of the universe. And you would want to have like weights on the fabric to show where the masses are. And then you could take what is the visible mass, and that would sort of cause a certain amount. And then you would like pull it down with like string, or I don't know, something like that, to show the extra mass. Like the overdensities and underdensities in the cosmic microwave background just do not match what you see. So again, there has to be some kind of missing hidden matter there, or we don't understand how gravity works at the largest scales. Like both of those are viable, although it's like really hard to explain gravitational lensing with like a re-understanding of gravity. We just reported this week in Universe Today that astronomers have found a dwarf galaxy with about the mass of the Large Magellanic Cloud, but it has no stars, or almost no stars. It's mostly dark matter. And so it is visible through the way that it warps the light behind it, but it doesn't have any illumination coming from the stars inside of it. So those are not theories for what dark matter is. They're just observations. But you're gonna want to say, what is it? Like, you're gonna want to make a falsifiable prediction for what that is. You can be like, well, like, what could it be? It could be a particle. Okay, what kind of particle? Well, particles are gonna have these kinds of behaviors. Let's look for the particle. We didn't find it. What else could it be? A different kind of particle. Okay, great. What kind of behavior would that particle have? Let's go look for it. No, we didn't find it. But the observation is still there. Like, just because you failed to find the explanation doesn't make the observations go away. And that is, I mean, that's the mystery, and that's what makes it exciting, and that's what makes it interesting. And I really think, like, when people make comments, and, you know, maybe this wasn't your intention, but when people make comments, you know, it's like, oh, like, why do astronomers just gotta make up this dark matter thing? They're not making it up. Like, they just keep seeing this everywhere they look, and they don't know what it is, but they know it's there. If you want to support the work we do at Universe Today, consider joining our Patreon club. This support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Funky Luiso, Jeffrey Zierl, James Drago, Robert Tucker, Mike Rivers, Robert Clark, John Mather, Michael Savuto, Phil Thompson, and Carter Nield. Join the club at patreon.com/universetoday. Kai, can you explain the debate regarding the presence of phosphine on Venus? If we have trouble gathering definitive spectrometry data on neighboring Venus, how do we do it with exoplanets? That's a great question, and there is not a good answer to this question. The idea of phosphine, which was announced a couple of years ago in the atmosphere of Venus, was really exciting because phosphine is one of these possible biosignatures that astronomers just haven't figured out a way that a planet could generate this stuff in the kinds of concentrations that they saw in the atmosphere of Venus. And so this is exciting. Like, on Earth, we know that phosphine is produced by life, and we have phosphine in the atmosphere of Earth. And so there doesn't seem to be any kind of non-biological way that phosphine could be produced on Venus, and yet they found phosphine in the atmosphere. Life found, except, of course, the evidence was inconclusive, that as soon as people found it, other people looked at the data again and found that the error in the observations were probably too great, that the signal wasn't strong enough, that it wasn't enough to be conclusive. And to add on top of that, you know, as soon as people say there's no way that rocks and such can make this kind of chemical, people figure out ways for that thing to make that chemical. And so you're always sort of back to square one. And I think what you're getting at, and this has been a theme that I've talked about on many of the interviews with Venus researchers and exoplanetary researchers, is that to have a definitive, conclusive discovery of something on another planet is going to be really, really tricky. Like, the signal has got to just be screaming at us from across the cosmos that there is life on this planet on so many different levels. Like, it's got to have all of these different chemicals, oxygen and methane and ozone and it's got to have like the right kind of signature for plant life on the surface of the planet. Like maybe it's got some chlorofluorocarbons in the atmosphere as well. And maybe we can see the city lights at night on the planet, and we're receiving SETI messages from them, radio signals coming at us. And when you think about how difficult it has been to confirm the discovery of phosphine on Venus, and Venus is right there, compare that to an exoplanet that is 10 light years away, 100 light years away. With Venus, we can send a spacecraft. It can go into the atmosphere. It can float around like a balloon and study the atmosphere. But we will never be able to do that with another star system. So, like, we all want that big discovery. Like, we found life! But I would be amazed if it was absolutely certain in my lifetime. And yet, we have to keep trying. You know, the best time to search for life was 50 years ago, and the second best time is now. So let's search for life. Chris Mitchells. I first heard of Lagrange points when Webb was launched. Could they fit multiple satellites into one point, or after a satellite is there for the spot spoken for? Lagrange point question. Let's do it. Now, I, of course, have done a whole series of episodes on the Lagrange points, but you are brand new to this channel. You are fascinated by Lagrange points, and I don't blame you. If you look for our next live stream, it is a picture of Lagrange pointing to me. That is how much we cover Lagrange points here on this channel. So there's 5 Lagrange points. 3 are lined up between the Earth and the Sun. 1 on the other side of the Sun, 1 on this side of the Sun, and 1 on the other side of the Earth. And there's similar ones with Earth, Moon, etc. And then there are points ahead of and behind the Earth in orbit. It's L4 and L5. 3 of the Lagrange points are unstable, which means that if you put a spacecraft into L1, L2, or L3, it will drift out and float away. The other 2, L4 and L5, are stable, so you could put a spacecraft there and they'll just hang out in that region forever. But they are not points, they are blobs. And that's because the distance, like the actual Lagrange points, are created by the interactions of gravity between the Sun and the Earth, or between the Earth and the Moon, or between the Sun and Jupiter. But the distance, say, from the Earth to the Sun changes over the orbit of the Earth. And so where the Lagrange point is shifting around as the Earth is going around the Sun and getting closer and farther from the Sun. And then at the same time, you've got the gravitational interactions of the Moon, you've got the gravitational interactions of Jupiter and Mars and all these things. And so it makes the Lagrange points a messy place. And so they are big. Like, you could be within hundreds of thousands of kilometers of each other. Like that's the kinds of scales that you're looking at. Well, maybe with the unstable Lagrange points, maybe within tens of thousands of kilometers of each other. But for the stable ones, like the L4 and the L5, like they're really big. Like you could be 1,000,000 kilometers away from another spacecraft and you're both orbiting within the Lagrange point and it's perfectly stable. So there is a bottomless room to put stuff into the Lagrange points. Sven Rastrup Anderson. Will one star in a binary star system be able to shred the other star to pieces when going supernova? What about the planets? Could they be thrown out of the system? If you've got 2 large stars orbiting one another, or like one large star and a smaller star orbiting one another, and the really massive star is going to live a short life, it's going to blow it up as a red giant, and then it's going to detonate as a supernova. And what's going to happen to the other star and its planets in this environment depends on a bunch of factors. So one factor is just how closely are they orbiting each other? Like if they're orbiting too closely, then when the one star becomes the red supergiant, its atmosphere could envelop the other star. And so that other star might spend a very long time inside the atmosphere of the red giant. And in some cases, the gravitational friction may pull that star inward into the red giant and destroy it. But there seems to be examples of stars that have been able to survive being inside the atmosphere of their partner red giant star, which is kind of amazing. In fact, there appear to be evidence of planets being able to survive this process. So you'd think that when a planet is orbiting a star and the star expands out and gobbles up the planet, like that's it for the planet. But actually later on, the star shrinks back down again and the planet's still there. So this has been observed, which is pretty mental. But when the star goes supernova, we say that you don't want to be within about 30 light years of a star when it goes supernova. Like, it's a bad day if that happens. But in the case of a binary star system, your star is going to be 100 astronomical units away from the star when it goes supernova. Like, you are getting a front seat. The explosion is going off in your face. And so it won't necessarily destroy the star. It will definitely be a bad day for any of the planets that are orbiting the star. Like, it's not a survivable event. If you're orbiting a star and the star is orbiting another star and it goes supernova, it's game over for your planet. What happens to the star? Well, it all depends on what happens to the massive star. So if the star is like not super massive, like say maybe it explodes and then becomes a neutron star, well, then it's still, gravitational interaction. It's still part of the binary pair. It exploded, but now it's still there, and it's still, it and the binary star are still orbiting one another, and astronomers see this. They can actually see examples where you've got a star that's orbiting around a neutron star. And so at one point in the ancient past, it was a massive star with another star orbiting it, and now it's a neutron star, and so clearly the star survived. But there's another class of stars, like when white dwarfs detonate as supernova, they just disappear completely. And so before, you had these two stars that were orbiting one another. One explodes as supernova and is gone, and so now there is no gravitational anchor to the second star, and so it just heads off into space. And that might be an explanation for some of the hypervelocity stars that have been observed. Astronomers have seen stars that are going 1,000 kilometers per second leaving the Milky Way, and that's an escape velocity, so they're never coming back. And that may be because they were in a partnership with a white dwarf that exploded as a supernova. And then the other class of really massive stars, like if you get a star that is 50 times the mass of the sun, 100 times the mass of the sun, it's believed that when they explode, they also leave no remnant behind. And so the star detonates and it's just gone. But that had an enormous amount of kick. So it's really like a slingshot. And then the other possibility is that that massive star detonates and becomes a black hole. And now you've got a black hole with a star orbiting around it. And we see examples. In fact, the first black hole ever discovered, Cygnus X1, was found because of the X-rays that were coming from it through its interactions with its stellar partners. So there's a lot of outcomes for what will happen when you've got two stars in a binary situation. None of them are good. So do not be part of a binary star system with a star that is destined to go supernova. That's my advice. Pavel Zersky, where's that future full of wonders that we've been promised by the futurists of the 60s? Where's my flying car? It's funny, like, I'm so deep in reporting the news that's coming out in space and astronomy that I can't keep up. I mean, it's my job to keep up, and so I keep up the best I can, but it's now about 20 stories a day that I feel would be interesting to tell you about. And then I have to boil that down to probably about 10 stories a day that we work on with Universe Today. And then we report on about, say, 40 to 50 stories a week. And they are mostly incremental improvements, but over time, all those incremental improvements make for gigantic changes in sort of our understanding of the cosmos. And then you think about the other kinds of improvements that are happening in material science, like solar panels are expected to be the dominant form of power generation, the electrification of everything, computers, cell phones, satellite internet, artificial intelligence. Like, it's kind of amazing how much all these things are rising. But I think part of it is that we are just, like, it's not the things that people in the past thought were going to happen with flying cars and personal jetpacks. It's stuff that's different. It's stuff that actually happened. And yet the stuff that actually happened are transformative. And yet things are very familiar. Like, if you took a person from the 1800s and brought them to the 1950s, they would just be baffled at the changes that have happened. But yet if you took a person from, say, the 1950s to now, they'd be like, things are different, but I get it, right? They'd understand how television works. They understand how radio works, and they'd be able to use a cell phone. It wouldn't take them long to get up to speed. And so it is interesting how a lot of the changes are less dramatic and yet do feel like they're big changes. I don't know. But I think we are on the cusp of a big step, which is the integration of artificial intelligence into everything. That everything is going to be smart. and it's going to feel very bizarre to be interacting with everything being intelligent. And I don't think we understand what the implications of that are, with the technological singularity. So we'll see what happens. Adam Shep. Is the L3 Lagrange point useful for anything? Oh, yes. So the L3 Lagrange point, this is the one that's on the other side of the sun, or, with the Earth, moon, it's on the other side of the Earth from the moon. And so the problem with the L3 point is that you can't reach it. You can't send a signal because you have to go through the sun. But that's a benefit. So one idea is, like, when we think about the Project Starshot, you want to create this laser that is so powerful it could scorch parts of the Earth from halfway across the solar system. Well, how are you going to get an international group of countries to agree to put this incredibly powerful laser system out in space where it could zap anybody's city? You put it on the other side of the sun, and because it's at the Lagrange point, it can never see the Earth, and so it can never be used as a weapon, but it could still send spacecraft out into space. So that's one cool idea. The other thing is that being on the other side of the Earth would give you, back to that original question about near Earth objects. If you're on the other side of the sun, you are exactly on the opposite part of the sun, and now you're able to see the rest of the sky. And so from one perspective, you're able to see half of the sky, all the dangerous near Earth objects, and then from the other side of the sun, you can see the rest. And so you're going to have to relay your communications around the sun to be able to get back to Earth, but it can still be possible. But the idea that I like the best is, we're all fans of interferometers around here. And when we think about, say, gravitational wave observatories or the Event Horizon Telescope, the bigger the distance between your telescopes, the larger baseline you're creating, the larger, so better resolution you can get from your telescope. And so if you could put one telescope at the L4 point, and then one at the L5 point, and then one at L3, you're creating an equilateral triangle. Great big triangle in space where they are all, and I forget the distance, it's like 200 million kilometers across, and yet these three places are relatively stable. Like, you need almost no fuel to maintain in the L4 and the L5, and you need some fuel to maintain at the L3. And people have done math that the way the Earth's movement goes around the sun, that you can maintain the position of those three observatories within a few hundred kilometers of each other, like maintain their positions all the time as they're all drifting around in their separate regions. And so you would have this telescope that is as big as the Earth's orbit. Can you imagine what we could see with that? Gravitational wave telescope. And I actually did an interview on my channel with someone about this idea that, how do we take Risa, which is designed, I think has arms that are like 15,000 kilometers long. How do we make a version of Risa to find gravitational waves, but we make the arms 200 million kilometers long? That would be better. So I'll put a link to that in the show notes. All right, those are all the questions that we had this week. Thank you, everyone, for putting your questions into the YouTube comments or wherever you put them on that billboard. I saw that. Again, reminder, we record this show every Monday at 5 p.m. Pacific time. So if you want, come join the show live. All right, I'm going to talk about my absolute obsession with the video game RimWorld in a second. But first, I'd like to thank our patrons. Thanks to Mark Anstis, Joel Yancey, Antonio Lofi-Lara, Dustin Cable, Just Paul Davis, Vlad Chiplin, Jay Dennis, David Gilton, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Veriboff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level, and all of our patrons. All your support means the universe to us. So, I play a lot of video games, but the one that I just keep going back to is RimWorld. It's an amazing game. I think it is the finest video game that's ever been made. Obviously, everyone's going to have opinions that disagree with mine, but I think objectively they're wrong. That RimWorld is the finest game. It allows you to create this colony where you have crash survivors who are attempting to eke out existence in a hostile planet, and yet so many weird, intricate things happen where you have pets and the people have interactions with each other, and they are being raided by barbarians, and you have to deal with droughts and blights, and all the while you're trying to build a spacecraft to escape the planet. And that is just like the base game. And then they've added psionics, and they've added genetic manipulation, and they've added ideology, and there's all of these great improvements to the game. But just at the heart of it, it is absolutely like I'm way over 1,000 hours of time on my Steam library with RimWorld, and I still am endlessly entertained by this game. So if you're looking for a game that will destroy all your free time, but can teach you some stuff about how to optimize your life, like I've learned valuable life lessons from playing RimWorld, so I highly recommend it. Now, please keep your video game recommendations coming my way, as well as your book recommendations and TV shows and things to watch. I am still a avid consumer of all things media. All right, thanks everyone, and we'll see you next week.